But one thing that jumps out at me here, Michelle, is that it looks as though as the qubit is sitting in Bob's location and then sitting in Alice's location, Bob's location, boy, the fidelity really degrades there. It goes from, you've got a great fidelity of 0.99 and drops down to 0.905 just over in Bob's location. And I would assume that's the memory itself. Is it possible that maybe we look at the vendor, the manufacturer of that memory, and say, do you have a little bit of a better maybe decay time or decoherence time available? Or maybe it's a different vendor that we select that has a better decoherence time. Is that possible? And are those things that we can actually choose from and get better parameters there to load into our model?
Yes, exactly. Let's go ahead and do that. We can try to simulate a better performance quantum memory and see the results that we get. So let's go back to our script, and okay, let's say that we're getting, we're trying to simulate a better performant quantum memory that has a better coherence time. So why don't we use for the defacing time 10 milliseconds this time? So this is going to, this is going to mean that it's going to take longer for the qubit state to be affected by the noise, right? So here, doing this, we are effectively simulating a better quality memory. So let's go back and run our simulation again.
So this may be a memory that maybe is a little more expensive, maybe based on our use case. We need, more coherence. We need the qubits to last longer in the memory, whatever it might be. And we're making those adjustments to get the best possible outcome here.
Yeah, exactly. That's right, Mike. Okay. We have our third log file here generated and our data collector output file. And okay, let's take a look at this. This is looking very, very good. What do you think, Mike?
Tremendous improvement. This is great. And so, looking at this, the fidelity starts at 1, obviously, drops to 0.99. And even at the end here, towards the end of the, the ping pong test, it's still at 9.97, 0.969. So it looks really good. This looks like a system that would be, I'd feel comfortable deploying for just about any use case. I feel like whether it's key exchange or quantum sensing, distributed quantum sensing, it's a great model. So this is a great example of the use case where I'm in the lab, I'm going to test out components and fiber optic profiles and run them here on my workstation without actually having to go out and procure, buy fiber optic cable, go out and buy memories. I can actually do all that work and end up with an outcome without having to spend really any money at all on devices or anything like that. Fantastic.